GameSci.com. GameSci.com.
Heidi ho, neighborinos. Welcome to Database and Records. What we're going to do is create a database to track online game user accounts. This is a very simple game scenario. Your game needs to track who is logged on. Duh. When the user signs up for a game, a record containing their email address, their player ID, their screen name, etc. is created and written to a file stored on the disk drive. Each time the player logs on, you must read their record from the disk file. Each time the player logs off, you must write any change to the record on the disk. So it comes time to create a new player account. You collect the user's information and you write a new record to your disk file. Now, every time the player logs on, you read that record from the disk file into RAM memory. The player plays the game. If any changes happen during the game to the player's data, when the player logs off, make sure that you take that changed data and update the record stored on the disk file. Now, this video is going to kind of bridge us between disk files and databases. If I'm programming a small standalone game, I'm probably just going to write disk files to my local hard drive. Once the game gets big, like a large multiplayer online game, then when that data gets large, I definitely want to use a database. So a small amount of data, use disk files. Large amount of data, you definitely want a database. Let's get started on creating our database. A database is a collection of records. If 1,000 players have signed up for an online game, there'll be 1,000 records in the database. I'm only showing you 3 records in this example. The ... simply implies there's more records. The ... on this side means there might be some more data in each record, and the ... along the bottom say there may be more records than the 3 I'm showing here. A record is a collection of fields, a set of information that describes something. In this case, an online game player. Records in a school database would describe a student. Records in a car dealer's database would describe a car. Now, in our game example here, I'm only showing 5 fields in this example. These extra dots means there may be more fields in this record. These extra dots at the bottom may mean there are more records. For disk sectors, the number of bytes in each record is very, very important. What's really critical to understand is how many bytes of data stretch from here to the end of the record. Does it take 100 bytes to store this data? Does it take 250 bytes to store this data? You need to know the size of each record. A field is a piece of record. It's a column in our data. It could be a string, an int, a double, it could be a variable. For a database, one of the fields needs to be what's called a key field, something that uniquely identifies the record. Email, or field 0 right here, is a good identifier key for 2 reasons. Number 1, it's usually unique. Everybody has their own email address, and people remember their email address. If you use this as their logon name, they'll always remember what their logon name is. A field is a piece of a record. This could be a string or an int. Obviously, it's a string over here. This definitely could be an int. It could be a double. It could be a variable, to be honest with you. This is the play ID, or field 1. It's the player's ID number that uniquely identifies the user. This number is typically needed for billing or accounting purposes, but it makes a terrible logon name because nobody remembers their player ID number. Internally, this is usually generated so the accounting department has some way of uniquely identifying each player other than the email address. A field is a piece of a record. Again, it could be a string, an int, a double, a variable. Here's the rest of the fields in our records: a screen name, a level, what level of the game are we on, and money. This could be virtual money or actual money that the player has played. The ... dots at the end here indicate there could be more fields in this database. We just don't have room to cover everything that you might store in this game player record. In total, the fields describe 1 player in the game. A numeric field may be stored as numbers or ASCII strings of characters. Most important is how many bytes of data one record occupies. It's up to you as the designer. Do I want to store these as integers? Is that an integer? That's an integer. Do I want to store this as a double variable? Maybe, maybe not. Probably the easiest way to do it is treat everything as characters. Then when you extract it, convert it to a double or an integer. But more importantly, how many bytes does it take to represent one record? Creating a data file on disk is a simple database. Let's talk DB terminology first though. A relational database stores information in a row and column format. When you extract information from a database, what we've been calling a record is a row from a relational database. And what we've been calling a field is a column in the data. Keep in mind we're learning databases from bottom up. We're kind of learning how to build a database from scratch. Here's how you format the data files, and then once we understand how to do that, then we'll go on and look at databases in full. So the first half of these slides we'll be looking at reading and writing our own database files. In the second half of this lecture, we'll look at using a database to do it. Back to disk files. A critical step in storing data in a database is converting a record to an array of bytes. Some decisions need to be made before you do this. Are letters going to be stored as 1-byte ASCII characters or 2-byte Unicode characters? Are numbers stored in integer or double format or as strings of letters? The easiest way to do it, the easiest solution is to store plain text. Then convert the letters, like 42.23, the letters 42.23, to a number after you load the data from the file into RAM memory. Hard disk drives are something that's called block addressable. This means an entire block or sector of data must be read or written at a time. Disk blocks come in sizes of powers of 2. Typically in the old days it would be 512 bytes per block on the disk sector. Optical drives tend to have a disk sector of 2048. And modern hard drives tend to have a disk sector size of 4096 bytes. Now, you cannot just read 8 bytes of data from a disk. If I just wanted to read bob@yahoo.com off a disk drive, it is not going to read just that. It's going to read a whole block of data off the disk drive. So understanding the size of that block is important for how you format data in your disk files. You want to nicely format your records inside of the disk blocks. Let's say a disk sector is 512 bytes long. You have to read all 512 bytes and then extract the 8 bytes you'd like. So it's important for efficiency, for speedy access to the disk drive, to read entire disk sectors at a time. And it does involve a little bit of math. Let's just say, for instance, that each one of these records contains 128 bytes of data. Let's do the math. If our hard disk sector size is 512 and our record size is 128, that means 512 divided by 128, we can store 4 records per disk sector. A data bucket says take the sector size, divide it by the record size, and your bucket can contain up to 4 records per sector. In this case, if all 3 records above were in the same bucket, there would still be room in the bucket for 1 additional record. What we're going to try to do is efficiently pack each of these records into a single disk sector. What if I had a different number of bytes per record? What if I had 64 bytes per record, or 256 bytes per record, or 512 bytes per record? Well, it depends on your disk sector size now, doesn't it? Do the math. If my sector size is 512 and my record size is 64, it means I should pack 512 divided by 64, or 8 records per sector or bucket. What if I had a sector size of 2048 and a record size of 512? What would I do then? I would divide 2048 by 512 and I would try to store 4 records per sector or disk bucket. The record size is important, as well as the field size. You always try to pack the records into each disk sector so they nicely fit in there and you can more efficiently extract the data from the disk drive. Now, if you are creating the database yourself, if you are writing the files to disk, you really need to worry about this. But the good news is, once we move on to databases, the database will handle this work for you. So let's say I have a sector size of 4096. Modern hard drives typically have a sector size of at least 4096, and I have a record size of 256. Well, I do the math, divide those two numbers, I can store 16 records per sector or bucket. And I should try to store 16 database records into each disk sector. Whew. Is that math traumatizing you? I know sometimes students get very traumatized by math. I'll never forget once I was having an exam and I passed out the exam and I warned him, hey, there's going to be a little bit of math on this exam. And the student said, can I use my calculator? And I said, no, you can't use your calculator. And right there in the front row, the student cried. And it wasn't hard math. It was this stuff of math. But they cried. And I feel bad now telling you that story. But, you know, if you're going to be a computer scientist, you need to know at least a little bit of math. So let's do a little bit more and then we'll move on. You can do the math backwards too. What if you want to store 8 records per sector? What if you want to store 4 records? Instead of looking at the record size first, let's decide how many records per sector to store. What if we have a sector size of 512 and you know there's 8 sectors per? You know 512 divided by 8, each record must be 64 bytes. Doing the math again, let's say our sector size is 2048 and we know we're storing 4 records per sector. If you divide those two numbers, you know that record size must be 512 bytes per record. One last example. If you know the number of records stored per sector, take the sector size, divide it by the number of records per sector, and that will tell you 512 bytes per record. Now, what do you do if the records don't exactly fit? What if the record size and the sector size don't allow for an exact match? The best thing to do is to leave a little extra empty space in each disk sector or disk bucket, as I've been calling them. Much, much better to have unused space on the disk drive than it is to try to span records across disk sectors. Let's say you had a sector size of 512 and a record size of 100. What would you do? Well, that one's pretty easy. You would store 5 records per sector and use 500 bytes. You'd have 12 unused bytes left over. What would you do with the 12? Well, number one, you'd leave them empty. You'd much rather have a few empty bytes in a sector than try to write records across different disk sectors. So the option number one for those 12 free bytes is just to put them all at the end of the sector. So my individual records would be at byte 0, byte 100, byte 200, byte 300, and byte 400. And there at the very end of the disk sector, there would be 12 free bytes of memory. The second option would be to add 2 free bytes to the end of each record. You never know when you might need a little bit more information stored in there. So it might be nice to have a couple of free bytes at the end of each record. I'll create record size of 102 bytes per record, and the 2 at the very end will be empty, and they could be used for something in the future. So then my byte offsets for each record would be byte 0, 102, 204, 306, 408. And even after all that, I'd still have a couple of extra bytes at the very end of the sector to fill out the 512 bytes. The moral of the story here is don't get greedy. Pack in as many records as you can per disk sector, but if there's something left over, leave it empty. Relational databases. Let a database do the work reading and writing disk files. If you're writing a small standalone program and it's going to keep a data file like saved games, then you use a disk file to do it. If you want it to be efficient, you have to worry about sector sizes and record sizes. But if it's a small amount of data, that's doable. But when your data gets big, when your data starts to span different computers, once you start getting into the online web-based games, now you're talking about using a database. Now that we've covered reading and writing files, the next step is to use a relational database program to handle the reading and writing of the files for you, so you don't have to worry about sector sizes and record sizes. It does all that work. But keep in mind the comma separated or fixed length record formats we've studied in past lessons, because that is how programs like MySQL, Oracle, or Microsoft SQL Server store the data in tables. Here's a logical view of a relational database. A relational database is composed of one or more tables. Each table will contain data in row and column format. And you can have multiple tables per database, and each table will have its own set of row and column. Usually each table gets its own disk file out on database. Finally, this third table, or table 2, has its own set of rows and columns. Now, why would you have multiple tables? Take this website, for example, my website. I have a table for the homework results. I have a table for the exercise results. I have a table for the quiz results. Every different type of scoring assignment I give you, I have a table where I store the results in it. The good news is all of these files on disks are handled by the database manager. DBM is short for database manager, and it handles the reading and writing of files to the hard disk. I think we're ready to start moving towards databases rather than reading and writing our own files to disk. Let's start with 3 records. Let's insert 3 records into the same table of a database. Now we're going to do this from a logical standpoint. I'm not going to get into code just yet. I need you to understand how they work before we start writing code to put data into a database. So let's just do a broad overview of how relational databases work, and then we'll get into the code next lesson. Data is stored in tables. The database manager, or DBM, handles all the details of storing the data in the files. But you do need to understand how tables work and how files work to really understand how a database works. Each record contains one or more key fields that identifies the records. For example, bob@yahoo.com could be a unique identifier that identifies this user in the database. You could also use something like this player ID field, 12345. If it's unique, that can be used to extract data from the database. And of course, the data is laid out in rows and columns. Each row is one individual entry into our database, one user of our online game, and each column is a piece of information that describes that record. So we see bob@yahoo.com happens to be at level 4 of our game. Get used to this row and column format. We'll be looking at it a lot. Now, what's the database have to do in order to achieve the speed and efficiency we need to do? Well, the first thing the database has to do is be very efficient on how it stores the data on disk. We talked about it on the previous slide there. It's got to be able to format the data into disk sectors. Disk drive has to read an entire sector at a time. If you scatter the data across disk sectors, it's going to take much longer to read than if you isolate it in its own disk sector. So let's insert bob@yahoo.com, add a new record to our table. The database will have some sort of insert function that takes the key and decides which disk sector it belongs in. In this case, it's decided that Bob belongs on disk sector 123. So underneath the covers, what the database will do is it'll read sector 123 into RAM memory. It'll go out to the database file and read sector 123 in RAM memory. It will look at the disk sector, and if there's free space for Bob, it will insert Bob right there. Now, we're just starting to load the data into the database, so all the records are free. We copy the 128 bytes of this record. This whole record gets written to the first 128 bytes of that disk sector. Once we have put it into our RAM buffer, what do? We take our disk sector 123 and write it back out to the disk file. All in all, it took us one disk sector read and one disk sector write, And this is what we call an order of one insert. Now we still have plenty of room left in that disk sector. Just for argument's sake, let's say when we insert tom@gmail.com, we add a new record to our table. We call the function insert, and it says, you know what? I'd really like to store Tom in disk sector number 123. So what do? We read disk sector 123 into RAM memory. Here's our disk sector read into RAM memory. Ooh, I should have labeled it. This right here is one disk sector of RAM memory. This is data that's being read and written to a disk file. Got 123 into RAM memory. We'll linear search this data and look for an open record. We find an open record and we insert Tom, the 128 bytes in Tom's record, into that location of the sector. Copy the 128 byte record at offset 128 into the disk sector. Once we've copied the data into RAM memory, what do? We write this whole disk sector back out to the database file. What about these empty records down here? We've got 2 occupied records here. We have 2 empty records here. Usually you put spaces or null characters in there to indicate they're empty. So you look at the bytes at the beginning of the record, and if there's spaces or null, you know it's a unoccupied record. If it's not a space or not a null, you know it's an occupied record. Time to insert a third record into our database. So we'll call the insert method and pass it our key. This is the unique key to identify the record, and we'll add a new record to the table. Now it turns out the insert routine, I'd really like to store Sue in sector 123. So what happens? Once again, we go out and we read sector 123 from the hard drive into RAM memory. Once the data is in RAM memory, we linear search down the sector until we find an open slot. When we find an open slot, we'll copy the 128 bytes that represent Sue into that sector at that point. Once that's completed, we've modified the sector in RAM memory. What do? We write that sector back out to the disk file. Right now, at this moment in time, we have 3 used records within our disk sector 123 and 1 empty record in the bucket or disk sector. Now once I've got my data loaded into my database, what do? I need to search and start retrieving the data for the users. Someone has come online and they said, my name is Sue at iCloud.com and I want to log on to the database. So now it's time to find that information stored on the disk drive. We need to retrieve a record from the very same table that we just loaded. So we'll go out to the find operation and say, where should Sue be located? And it returns 123. I expect to find Sue in sector 123 of the database. So we read sector 123 into RAM memory. And the first thing we do is we look at the first record of the sector. And if you compare Sue to Bob, it is not a match. When it's not a match, we got to keep going. At this point, what we'll do is go on to the next record in the sector. This is what's called a linear search or a linear probe. We already know that Sue should be in sector 123, and sector 123 is in RAM memory. If we didn't find Sue in record 0, or at the very beginning, we need to advance to the next record in the disk sector and check to see if that's Sue. And it turns out we find Tom. Sue and Tom are not a match. So we're going to continue the search of the bucket until we find our data or we find an empty record. This is called a simple linear search or a linear probe. We're still doing the same operation. We're still looking for Sue in our disk sector. We know it's in sector 123. We're searching for Sue. As we go through our data, sector 123 is already in RAM memory, and then when we get to byte 256, we do find a match for Sue. That's the data we're looking for. We found a match. This will stop the search of the disk sector and return the record the user is requesting. Return the entire record at byte 256. Each of these records take 128 bytes. Return all of these bytes to the user. And this is called a simple linear search or probe. and it's what the database does underneath the covers for you. Now let's do something completely different. Let's do a find of something that isn't in the database, xxx@icloud.com. We want to retrieve a record from the same bucket, but this time it's a record that is not in the database. So, just by coincidence, no, not by coincidence, by design I made it that way. The find function said you should find this address in disk sector 123. So sector 123 is loaded into RAM memory, if it's not already there, and we're going to search that record for xxx@icloud.com. We search Bob, we search Tom, no match, we search Sue, no match. However, we run across this empty record at the bottom, and that empty record is a signal that it's not found. We're going to return not found because we found an empty record. It's not in the database. Not all searches of a database are successful. You look at the disk sector, and if you start to find empty spaces, that's the clue that you're searching for something that is not in the database. However, if this bucket had been full, if there had been 4 records in this bucket, and I still didn't find my target, I would then have to go read the next disk sector and look for it there. The next major operation that a database does is called a delete. Remove something from the database. We insert data, we search for data, and we delete data. Delete a record from the very same table that we've been focusing on. Now, it's no coincidence that everything is in disk sector 123. I just wanted to kind of see all the data at once. We go out to the delete command and say, where should Tom@gmail be? And it returns we should be in sector 123. So what do? The same thing we've been doing all along. We read sector 123 off the hard drive, we load it into RAM memory. Once it's in RAM memory, we'll do a bucket search looking for Tom, and we'll find it with this red line right there. We have found our key right there. Tom is at byte offset 128. Delete is a find first. It means find the data record first and then delete it. Careful removing the record. We don't want to mess up the search or find operation that we looked at. When we delete Tom, we are not going to make it look like a blank record. What we're going to do is something slightly different. The delete function has already returned 123 for Tom. Sector 123 has already been loaded into RAM. What we're going to do is replace the record Tom@gmail with a deleted flag so we do not have an empty record. That would mess up with the search. When we are searching for Sue in this database record, we don't want to stop here, right there. We want to keep searching for Sue until we find it or we hit an empty record. Empty records means the data's not there. A deleted record means keep searching for it. It might still be farther down in the sector. Deleting causes 1 disk read and 1 disk write. Again, it's a very fast algorithm. We can reuse the deleted space on a future insert. If we were inserting a new record into this sector and we spotted that deleted flag, we could overwrite it with new data into the database at that location. Insert, find, and delete. These are disk read and writes handled by the database manager, not you. I'm going into a lot more detail than we need to go into. I want you to understand what the database is doing down at the file level. That is a detailed description of how a database works under the covers. The good news is you don't have to be an expert on reading and writing files to use a database. But you do need to understand how it works to understand the logical view of a relational database. Given the time penalty of reading extra sectors, lots of free space is a huge requirement for disk storage on disk. We'd much rather burn some extra disk storage space than try to juggle records across different sectors. Also, to speed access, fixed length records packed into disk sectors is a needed requirement for any efficient database operation. A logical view of a database. Let the DBA handle the disk read and write. Now we can start to focus on the data. Pretty much every website in the world operates in a similar manner. The user makes a request, show me the controllers for sale, or videos to watch, or games for download. That request triggers a database query that extracts info from the database. Before sending it back, the data is nicely formatted with HTML and displayed to the user. So here you are on the client side. Let's say you're at Amazon.com and you say, I'd like to see game controllers for sale. That request is sent to Amazon's server side. A PHP program looks at your request and makes a query of the database. Out to the file it goes. The database manager reads the data off the disk drive and returns it, where a PHP program there on the server side formats that data for display and sends it back to the client. The client then displays it and shows it to you, the user. That's how almost all websites in the entire world work. Show me this, go to the database, retrieve it, format it, and show the reply to the user. Let the DBA handle the disk read and write. Let's focus on the data. From a logical viewpoint, just think of a relational table as a set of records, where each record is divided into fields that describe one entity in the table, like one player/user of an online video game. So here in record 0 is bob@yahoo.com, and this information in that record describes the player Bob. At record 2, we have Sue at iCloud.com, and the information in these fields describes Sue. And so on down the line. In record 5 is Mac at iCloud, and this is Mac's player ID, and this is Mac's screen name, and Mac is at level 5, and Mac has $87 of money. One record represents one player in our video game user database. A relational database stores information in row and column format. When you extract information from a database, what we've been calling a record is a row from the database. What we've been calling a field is a column. Some people call these rows and columns. Some people call them records and fields. You just got to get used to both terminologies. But when using a relational database, we kind of lean towards rows and columns. You can see I've got row 0, row 1, row 2, row 3, row 4, row 5. The data that goes horizontally along there represents one record. Individual columns or fields represent one type of data within the record. Now, what is a query? A query is a question, an inquiry. The foundation of a relational database is the ability to ask the database for data stored in the rows and columns. For example, if I were to ask this database, what are the play IDs stored in the table? It would extract this column of data and return it to the user and say, this is a list of all the play IDs in the database. Data stored in rows and columns, and what we do is we ask for specific rows or we ask for specific columns, and it is extracted and returned to the user. Foundation of a relational database is the ability to ask the database for data stored in rows and columns. For example, what rows have a level equal to 2? If that's the query, the database will search this data and say, oh, Tom is at level 2. And Tim at UCLA is at level 2. Extract these two rows, return them to the user, and say this is the sub information that you were looking for in the bigger table. You've got to think of these queries as taking a big input table, all of this, and returning just the rows that you requested. You do not have to access full rows and or columns. You can ask for very specific data in a query. For example, what are the screen name, level, and money where money is greater than 50? I almost wanted to kind of highlight the rows and highlight the columns and say, it's the intersection of these rows and columns. But I didn't want to get the slide too busy, so what I did is in red boxes, highlighted the specific columns that we asked for with the specific rows that we asked for, and what these three little sub pieces make up is a return subtable containing the data returned from the query. Does everyone see that? This information right here matches our query. We want the screen name, the level, and the money fields for just the rows where the money is greater than 50. And what actually gets returned by the query is this subtable of a limited number of rows and columns for our inquiry. I like to call it table in, table out. The table in is the entire data stored in the table. And what the query does is it extracts certain rows and columns and returns that as a subtable. Once the subtable is extracted, a simple loop through the return data displays the results to the user. This is how every website in the world behaves. Extract and display from the database a small subtable and display the small subtable to the user. If you're extracting game controls from the Amazon database, it's only going to show you those rows that represent game controllers. It's not going to show you the whole data in the database. Once I've returned it, I will then go through this data with a very simple loop and say, the first thing returned was Avengers 9 and $85. So the players making bank, there is the first row of the subtable that was returned by my query. And I'll just keep looping through the same data. Here is the subtable returned by my query. Go to Amazon, search for game controls. A subtable is extracted from their database, and then a loop displays the controllers for sale in order of highest probability. In this case, we've gone to our database and we said, extract for me all the players that have more than $50 of money. What I'll do is I will loop through that data and list out who's got the money, who's made the money most in this game. And Tim on level 2 has got $72.99. All of these are the people with money greater than 50. Keep looping through my subtable that was returned by my query, and there's a third record that was returned from the overall database. Big Mac on level 5 has $87 in the bank, so we'll print out the results there. This is how every database in the world works. It's quite simple from a logical view. They have a bunch of data stored in a relational database. You, the customer, come to the site and say, I want to see this. It extracts that information, creates a subtable with the information you're looking for, and then loops through it and prints out what you want. If you go to YouTube and search on PHP programming, I'm sure there's lots of videos on PHP programming in YouTube. It extracts a subtable of just the PHP videos, and once it's got it in the subtable, it will loop through and, like YouTube does, display all the videos that have PHP in them somehow, some way. Usually what every website does is they're trying to maximize money. So they're going to show you the videos in order from the highest ad revenue generated. If they have a PHP video that's made them a lot of money, that's at the top of the list, and they display it first on the output. If they have videos like mine that don't make a lot of money because I don't put a lot of ads on them, I'm going to change that. One of these days I got to cash in. Then they put those at the bottom of them. That's it. That's the way the world works. Amazon shows you their highest profit items before they show you the lower profit items. YouTube shows them highest profit videos before the lower profit videos below it. Behind every website is a database. Pages on that site are created by extracting a subtable from the bigger table, then looping through the subtable, creating HTML with the data for display. This is the concept I really want you to understand. We are storing a large amount of data in our database. We need to show the user some of that data, so we extract it using what's called a query. We get a subtable returned, and then we print the subtable and show it to the user. Boy, I think we're ready to get into real database programming. Hopefully you got the logical view now. Let's go to the practical view and see exactly how it's done. I'll see you in the next video.